Good afternoon, you all. Myself Sana Sheikh. I am a second year PhD student from IIT Bombay, and I am doing a NPTEL course TA ship. Uh, the course name is Mechanism in Organic Chemistry, and the course instructor is Professor Nandita Madhavan from IIT Bombay. On every Saturday from 3 to 5 p.m., I am taking a live session in which we are discussing the few questions based on the topic taught by ma'am in YouTube lectures. So as we have already discussed the Hammett plot in previous lecture yesterday only. So now we will think about the slopes which we are getting by Hammett's plot. So what about positively charged intermediate? So sometime based on Hammett equation, we know Hammett equation is log kx by kh equal to rho sigma x. So what will be the sign of rho here? So as we have look in the previous class, the positive slope is like this one, and we have compared the value uh, with benzoic acid, which we have discussed the less sensitivity and more sensitivity of the uh, rho value. So now here that was a case for negative charge raw value, but what will be the sign of raw for the positive what will be the condition for positive raw value? So today we will discuss that thing also. Now, so this is the reaction example given here. So which type of reaction is this? SN1, correct? Because here you can see tertiary carbocation formation will take place, and then that carbocation will be trapped by OH uh, manase to give the corresponding alcohol as a product. So this is a type of SN1 reaction, right? So SN1 reaction is that means if the this carbocation will be stabilized by electron releasing group or electron donating group. Can you think about it? So as all of you know that we are talking about here with respect to benzoic acid, and here we have the aromatic ring and substitution at para position. So suppose this para position substitution is electron releasing group or electron rich group. So what will happen? It will generate here negative charge, correct? We have already discussed. So it will stabilize the carbocation formation. So that means electron releasing groups are stabilizing the carbocation formation. So this reaction will be stabilized by carbon. So this reaction will be stabilized by electron releasing group. That means the raw value uh, will be uh, this electron releasing group will stabilize this one. That means raw value will be higher in case of electron releasing group. But here, because to avoid the confusion, we are always taking a negative for electron releasing group and positive for electron withdrawing group, but the magnitude will be high for electron releasing group. So here you can see we have 0, and here electron withdrawing group, and this side is electron releasing group, electron rich group. So as I told you, electron rich group will stabilize the carbocation formation in SN1 reaction. So because of stability, rho value will increases, correct? But the sign will remain minus because of to avoid the confusion. But you think magnitude of rho will increase. That's why here the slope will start from this point. As electronegativity, electron rich group is present, that means rho value is high. As we are moving towards the electron withdrawing group, then the slope is lowering down. That means that is destabilization is taking place in the reaction. Understood? I hope all of you are clear here. So what we have learned in previous class and today's we have already also discussed this last point. So this is a summary of our Hammett plot. So we have discussed that if raw value is greater than 1, then the reaction is more sensitive than the benzoic acid. Already we have discussed yesterday. This is the value of 1. This is called 1. if slope is more, sorry, if slope is more than this one, that means it is more sensitive. If it is less than benzoic acid, that means it is less sensitive, correct? Is less than 0, sorry, more than 0, less than 1, that means it is less sensitive than benzoic acid. If this was the case for intermediate, when the intermediate is negatively charged. But when the intermediate is positively charged, which we have discussed here, positively charged, that means carbocation formation is taking place here after leaving Cl group. This is the intermediate, correct? So in this case, slope will be negative, and the rho value magnitude will be positive, but the slope will give a negative value, negative sign, and the magnitude will be higher. So and we have discussed rho value is equal to 0, that means reaction have no substituent effect, that is straight line. We have already discussed in previous session. So this is all about rho values in Hammett constant, Hammett reaction. Now here you have to predict the rho value, sign and magnitude for the given reactions. So what will be the for probability? First we will choose the one case where both the R groups are Me, methyl group. So when methyl, both the R group will be methyl, then we have discussed in earlier case, here also both the group are methyl. So what will happen? SN1 mechanism will follow by the reaction to give the intermediate carbocation, tertiary carbocation. But the second case, what will happen be if protons, both the substitution R group will be H will be there, that time it will become primary carbocation, which is less stable. So here SN2 mechanism will be followed because of less steric hindrance, correct? So SN2 mechanism will be followed by the reaction in this case when both the R group will be H. Now you can see that both the rho values are negative only, but the magnitude is higher in first case compared to the second one. So as I told you, if we will plot the graph here, we have 0, here electron withdrawing, 0, electron releasing. Correct? And this is our Hammett rho value. Sorry, log Kx by Kh. Right? Okay. So here we have first carbocation formation in case of methyl. That means it will get stabilized by electron releasing group, right? It will get more stabilized by electron releasing group. So that's why it will give this type of negative slope. We have discussed already. Now the second case is here where the reaction is going through SN2 mechanism. Here there is no carbocation formation will take place, only this distributed charge will be there. So in this case electron releasing group will stabilize, but not that much compared to the carbocation here. So this is not that much stabilized by electron releasing group. So that's why, but electron withdrawing group can be stabilized, can stabilize this intermediate, right? Slightly. So that's why it will become this way. Sorry. Yeah. So electron releasing group not stabilize this one as much as compared to the first case SN1. So this magnitude will get reduced slightly. So this is the value for H1 and this is for methyl group. So which magnitude is higher? All of you know this one is higher, right? Correct. So this is how we can distinguish between the reaction by using the Hammett plot. Now again we are discussing the Hammett plots to determine the mechanism. So here we have one molecule and it's giving a reaction here. So with we can predict the mechanism for this type of reaction, right? The first possibility is that SN2 mechanism, right? In SN2 mechanism, nucleophile will attack and simultaneously chlorine group will be eliminated. Like this intermediate we will get, right? But if it will proceed via SN1 mechanism, what happens here? Positive charge will generate here, that means carbocation formation. Then that carbocation will be trapped by nucleophile. Okay, so that carbocation will be trapped by nucleophile. So in both the cases, can you see here if electron releasing or electron withdrawing group will be present on this phenyl ring, benzene ring. So will it affect the mechanism or not? So here it is given the raw value already. It is given, which is minus 5.09. So we will check here it's stabilized or not. So if electron releasing group will be present here, electron releasing, so all of you know that we have discussed electron releasing groups are stabilizing the carbocation generated on alpha position. We have discussed in previous example. So when electron releasing group will present, then it will facilitate the SN1 mechanism, right? It will favor the SN1 mechanism, but while in the case of SN2, if electron releasing group is present, it will not affect that much compared to the SN1. So as you can see here, Hammett value is given here minus 5.09. You know that means the effect of electron releasing group is high. That means raw value should be high and magnitude will be high only. That's why from this experiment we can conclude that the reaction is going via SN1 mechanism only, not by SN2. Correct? Okay. If any doubt you have, you can ask me in between. Now again we have one more example. Predict the raw value for the given reaction. So here you can see again we have a benzene ring, aromatic ring and epoxide. What actual mechanism of this reaction? What will be the actual mechanism? Here it's given already, right? So negative charge will attack on this alpha carbon of epoxide and it will get opened, and we will get the O minus as a intermediate, this as a intermediate. So here which group will facilitate the reaction? Suppose if NO2 or electron withdrawing group is present, so electron withdrawing group will stabilize this minus charge, right? You can check by previous session also. We have discussed in previous lecture. So if electron withdrawing group will be there, then positive charge will generate over here and it will stabilize the negative charge, right? So this species will be stabilized by electron withdrawing group present at para position, correct? While talking about the electron releasing group, when electron rich group will be present here, it will destabilize the molecule here, right? Then because molecule will be destabilized, the energy will be high. Stability is inversely proportional to the energy. All of you know that if the more the stability, less the energy. If stability is less, that means the energy is high. So here because an electron withdrawing group is stabilizing this molecule, that means its energy is also decreases. and in case of electron releasing group, energy is high. So we can see here in graph, this is the actual Hammett plot which we are taking as a standard, right? This is our standard. Now this is for X equal to H, not the electron rich group, not even a electron withdrawing group. So here when we have electron withdrawing group, the stability of the reactant is increases. That means energy will become lower. This is the Y scale is our energy. This is our energy. So energy will be low. While in case of the uh, electron rich group, the stability will be less. That means the energy will be higher, right? So this is the energy of electron releasing group. All these reactant have different energy stability, but the intermediate through which they are going will have a similar type of energy, because this electron releasing group and electron withdrawing group will not affect the intermediate as much as starting material. That's why the energy difference uh, between transition state will be very low. That's why here you can see, here the difference is very less, but here if you will compare, the distance is more, right? Here also. So from this uh, this plot, what you can conclude, that if you the reaction occur through this medium, this releasing group, the activation energy will be less compared to this one, right? If you will calculate the activation energy, you can see hill is that much height only, but the climbing for this height, the energy is more compare in electron releasing group. Like suppose you are at ground floor and you have to reach at 13th floor, right? 13 or 15, anything. Then if someone is climbing the building by with second floor, and so the other person is standing at fourth floor, who will reach first? All of you know that who is standing at fourth floor will reach first. Same case is here also. The activation energy means the time and energy will require more for the person who is standing at ground floor compared to the fourth floor person. So that's why this reaction will be more feasible, more easy. This will become more easy to reach the goal, right? Reach the transition state. So that's why when electron releasing group will be present, that time Kx will be higher than the Kh, because it's uh, favoring the mechanism to reach the intermediate easily. The energy difference is less. That's why this is the case when the electron releasing group is present, and when the electron withdrawing group will be present, that time you need more energy, more activation energy, means slow reaction, less favorable. That's why Kx will be less than Kh in case of electron withdrawing group, right? Now we can do the Hammett plot for this plot. Here you can see then electron releasing group are favoring the reaction. That's why it has high magnitude, right? And because electron releasing withdrawing group are lowering the slows the reaction, lowering the probability of reaction. That's why the slope is going this direction, right? So this Hammett plot is negative plot, but because it is more stabilized, that's why the value will come in negative, will show minus charge, but it is more stabilized by electron releasing group. So don't think whenever uh, negative sign is there, that means electron is not stabilized by electron releasing groups. This negative slope is also showing the reaction possibility with minus charge, because to avoid the confusion, minus charge is that mean minus charge is present, that means electron reaction is going through electron releasing group. Okay, then what we have discussed till now, we have discussed till now Hammett equation, which is log kx by kh equal to rho sigma x. We have discussed this equation, and Hammett plot was log kx by kh versus sigma. And from Hammett plot, we can get the information about the intermediate transition state, and we can distinguish between the mechanisms as we have done earlier, SN1, SN2 type of mechanism. Now, again, here we have one more example, like similar case. Here we have NH3 and positive charge is present on nitrogen atom, correct? When proton abstraction is taking place, you are getting this intermediate, right? So suppose electron withdrawing group is present here. So electron withdrawing group, if present here, it will give here negative charge, which will destabilize the reactant, because it's a nitrogen which is electronegative atom. So destabilization will take place. But if electron rich group is there, that time it stabilize the reactant more compared to the electron withdrawing group. Now, this is the difference between the electron withdrawing species and electron releasing present on para position in this reaction. So, because nitro group is present, that is increases the energy of the molecule by destabilizing it. So, the energy of nitro group will be higher, and because electron releasing group is stabilizing the molecule, the energy will be low, correct? Hmm. Yeah, so the energy will be low. So as we have discussed earlier, the height to of activation energy is easier for electron withdrawing group compared to the electron releasing group. So that's why in this case kx will be higher than the kh in case of electron withdrawing group, and kx will be lower than kh in electron releasing group. So what will be the graph here? Anyone can predict? Here we have 0, electron withdrawing group, electron releasing group. Right? So what will be the Hammett plot here? This way, positive slope, because in electron withdrawing group kx is higher than kh, right? Here suppose we have h, so kx is higher than kh, so we will get here positive slope. Got it? Now here is the application of Hammett plot. These things are already discussed by ma'am in YouTube lecture, but I'm just summarizing these things to solve the questions based on these topics. So here we have reaction which can be done by two different pathways. We can predict the mechanism by two different pathways. So here path A and path B is there. So now if the reaction will proceed via path A, where this nucleophile will attack on nitrogen atom, and yeah, sorry, here a nuclear OH minus will be act as a base, and it will abstract the proton from nitrogen, and double bond will occur here, which will results in a formation of this O minus ion, phenoxy ion, we can call as phenoxide. Now this group will be released by this reaction to give the carbon dioxide and primary amine. Then via path B, if the reaction will proceed via path B, this O manage will attack on carbonyl carbon to give the corresponding a tetrahedral intermediate, and that tetrahedral intermediate will undergo elimination to give the corresponding product. But which mechanism will be followed by the reaction, we have to predict this via Hammett plot. So as you can see, raw value is given 2.62, correct? 2.62. That is positive value. That means it is more sensitive compared to the benzoic acid according to the Hammett uh, Hammett principle, right? More sensitive. That means the slope is positive, like this way, correct? So that's why it's more sensitive. So if it's more sensitive, that means it will be stabilized by electron withdrawing group. So that means if electron withdrawing group will be present here, it will stabilize the molecule, correct? It will stabilize the molecule. So because it's stabilizing the molecule and it's more sensitive than benzoic acid, so the preferred and favored mechanism for this reaction will be your path A, not a path B. If you will see here, uh, if electron withdrawing group will present here, it will not stabilize compared to this one. Suppose we have here, we are getting this as an intermediate, right? So here, if electron withdrawing group is present, it will stabilize this negative ion, correct? It will stabilize very good nicely, but in this case it will be very far from the this effect ring, right? Negative charge is generated over here, which is very far from the electron withdrawing group, so it cannot stabilize that much compared to the path A. So according to the value, we can say it is more sensitive. That means this path A mechanism is a correct mechanism. So this is the application of Hammett plot, from which we can find out the correct or possible mechanism for the reaction. Hmm. Then now because we have discussed till here the Hammett plot, but because it's a benzoic acid as they are taking benzoic acid as a standard. So it's not giving because we are taking the benzoic acid as a standard this reaction, so it's not giving that much good relation compared to the uh, ben, sorry, am I audible? Sorry for the disturbance. So here we have talked about till here Hammett plot. But in Hammett plot we are taking the carboxylic acid as a standard, but if the case is different, like we have phenol. So in carboxylic acid what we are observing, it's a extended conjugation, or we can say uh, it's a distance from the para position to this charge species is very far, and it can predict uh, those relation only, those Hammett plot. But in case of the phenol, what happened? In case of phenol, it's a direct conjugation in aromatic ring, right? It is in direct conjugation with phenyl group, benzene ring. So that's why for this type of reaction or species, the new scale have arrived. So here we will discuss, because as I told you, it is a indirect conjugation with the phenyl ring. You can see it is highly stabilized compared to the carboxylic acid example, because as I told you, this charged species is very far from the aromatic ring, so it's the stabilized relation is not that much higher compared to the phenyl, phenyl group, phenoxide ion, sorry, phenoxide ion, correct? So that's why new scale have introduced, which is here sigma plus and sigma minus. So what is sigma plus and sigma minus? So if carbocation generation is taking place, that means uh, benzene ring is stabilized by sigma. I I will draw here first. Sigma plus. Suppose this is our benzene ring. Sorry, just understand it. And we have, suppose here, plus charge. Correct? Now this plus charge is in conjugation with this aromatic ring, right? And if electron withdrawing group is present here, sorry, electron releasing group, so it will stabilize the carbocation, right? So this is the case when the SN1 reaction mechanism will takes place. So you can see here, this is donating group, and because donating group is present, it will stabilize the carbocation. So because it's stabilizing, so the value will be higher and positive. So you can say this sigma value will be higher. That's why we are getting here 1.3. So all of you will ask question why we are getting minus here. So this is nothing but because to avoid the confusion. So you have to look at the magnitude. Magnitude is higher, but the negative charge is here to avoid the confusion, because we are always telling that on scale, negative side is electron releasing group and positive side is electron withdrawing group. So always we are keeping negative as a electron releasing group is present, electron withdrawing. So because electron rich group effect we are showing here, that's why minus charge is given here. Okay, so that means here NH2 will give the more stability to the carbocation at alpha position. While talking about the OH minus, it will also stabilize the carbocation. That's why the value is increases from para and meta position compared to para and meta position in Hammett plot. So this is the sigma plus value, which is increases when the electron rich group is present, which is stabilize the carbocation. But in case of the carbon anion like phenoxide, here this case, here negative charge is there, that means it will be stabilized by the electron withdrawing group, correct? Electron withdrawing group will stabilize the negative charge on phenoxide ion. So you can see phenyl group is present, so phenyl group will stabilize the negative charge slightly, that's why the value is 0.08 here, more than 0. So phenoxide ion will be stabilized by phenyl substitution here, correct? but slightly difference will be there. You can draw by yourself. Instead of X here, draw phenyl group, correct? You can change the substituent. Now while talking about the halogens here, so in case of halogens you can observe here inductive effect is more compared to the mesomeric effect. So while the inductive effect is increases, that time the stability of carbocation will be decreases. That's why the value is decreases here. You can compare the value, right? Inductive effect is more compared to the mesomeric effect. So now talking about the carboxylic acid, acetate and carbonates here, we will see here that sigma negative is increases. That means the electron withdrawing effect is increases, which is increasing the stability of the phenoxide ion, negative charge on alpha position of phenol, correct? So this is the relation, and sigma plus and sigma minus values relation between the electron rich and electron withdrawing group. Now this is a deviation from linear free energy relationship. So here the Hammett value is given minus 4.4 for electron releasing group and 2.5 for electron withdrawing group. So as here given here with Hammett value, you can see clearly that this is giving a negative slope and this 2.5 is giving a positive slope. That means more sensitive compared to the benzoic acid, right? Now we will see here difference in a mechanism. So difference in a mechanism will be here like if there are two possibilities. One mechanism is that when water will attack on carbonyl carbon and it will give a negative charge on oxygen, followed by the elimination of Cl group will give the benzoic acid, chloride group. Now the second case is there when this lone pair of oxygen will make a bond here and followed by the elimination of chloride ion to give the stabilized intermediate here, and this intermediate then again will be trapped by the water molecule to give the corresponding product further. So this is the alternate mechanism. Now which mechanism will be favored? So as you can see here, if we are talking about the electron releasing group, suppose first case we are taking here electron withdrawing group. So if electron withdrawing group is present, it will stabilize the here carbocation, right? It will stabilize sorry, not carbocation, it will stabilize this carbonyl carbon, and it increases the electrophilicity at the carbonyl carbon atom, which favor the reaction, means stabilize the reaction. So that's why the Hammett plot, which is 2.5, is for this favored electron withdrawing group, presence of favored electron withdrawing group. But the other case is more favorable because in this case here positive ion is generated on oxygen atom, which stabilize to give the plus charge here. So if electron releasing group is present here, it will stabilize this positive charge, right? Electron releasing group will stabilize. So this effect will be more compared to the first pathway. That's why this alternate mechanism will be the favored mechanism for this type of reaction, because it's more stabilizing the uh, plus charge present on alpha position. So that's why the value for this Hammett is minus 4.4 for electron releasing group. That means it is more sensitive. The plot will be like this one, and for this case, this 2.5, the plot is like this one. So the slope is more in this case, sorry, in first case. That's why it is a favorable mechanism, right? This is a further explanation here. Raw value is more than 0 in case of electron withdrawing group, as I told you, and here the raw value is less than 0, but the magnitude is high. That's why this is a favorable mechanism. So this is the Hammett plot which we have discussed. Slope is higher here, and then it will be less for electron withdrawing group. This is electron withdrawing group. So we have discussed here so far benzoic acid ionization, and where the constant was sigma, and which was giving a inductive effect mainly, and the reaction constant was rho. Here reaction constant was rho. And then we have discussed sigma minus, where it was stabilizing the phenol, and resonance and inductive effect, it was showing both the effect. So, and reaction constant was rho only. Then we have discussed the sigma plus also, which is the phenyl dimethyl chloromethane. We have taken the example, and we have discussed that reaction was going through SN1 mechanism. Sorry. Here we have discussed that if sigma plus is there, that is favoring SN1 mechanism and carbocation formation, right? We have discussed here. And resonance and effect, inductive, both the effects are there, and reaction constant is rho again. So this type of Hammett principle, this type of effect is also studied by the Yukawa, Suno, and Topsham variation, and they have mainly looked in the resonance and inductive effect. So ma'am have already discussed all the principles. So now we will discuss the Taft parameters. So what is Taft parameter? Es and sigma star are there. So we will discuss here. Standard reaction for sigma star is given. Like one example is given here. RCOOMe, which is undergoing reaction with water to give the corresponding acid. Hydrolysis. It's a hydrolysis reaction and giving the acid, right? So reaction suppose conducted in an acidic medium. Then what happens? First the protonation will takes place, right? Yeah, protonation. Then after the protonation, water molecule will attack at electrophilic carbon atom present here, carbonyl carbon, and it will give the intermediate, where you can see uh, H2O is present, positively charged, right? Because this step is a slowest step, it is a rate determining step. And after this one, it will get tautomerized, and elimination of HOMe will takes place to give the corresponding product. So proton transfer will takes place to make it the best leaving group to give the product. Now here you can see in rate determining step, that this step A and B, the charge on both the side is equal. Positive charge is here, and here also positive charge is there. That means this is the reaction condition where the it is not affected by the charge species, right? Charge is not affected here. But now the second factor we can talk about, which is steric factor. So while talking about the steric factor, if this R group is different, like suppose here we have me methyl group, this R group as a methyl group. So what happens here? Here the reaction will proceed, and this proton present on this methyl group will affect the reaction, right? It will affect the reaction it will create a steric hindrance. So from this term you can conclude that the if R group is bulkier or a larger, that will affect your reaction by steric hindrance. So here steric is important, right? So according to the top parameter, the equation is log kx by kme, where kme is a standard. Here we are taking if kx is less than me, smaller than me, that means, yeah, if kx is a larger group, if it's larger group, then the kx will be less than kme, right? If kx is a smaller group like h, kx is h suppose, then it will create a reverse effect. That means kx will be larger than kme. Kx will become larger than kme if small group is there. Small group means proton, correct? And es will become more than 0 in case of smaller group. That is more favorable, correct? Same like raw, in Hammett equation we are talking about raw. Here we are writing es, not sigma, es, right? So if the R group is bulkier, that means the kx is less than kme and es will be less than 0. But if the R group is smaller than methyl, that time kx is greater than kme and es is greater than 0. So this effect is mainly depends on steric hindrance in acidic medium, right? Yeah. Now let's talk about the basic medium. So in basic medium, what happens here? Because we are talking about basic medium. So in basic medium, OH minus will attack on carbonyl carbon, and it will give the, yeah, OH minus will attack at carbonyl carbon, and it will give the electronic steric intermediate. So here what will happen, because in start this is a RDS, means the rate determining step, and here you can see we have a charged species at intermediate, right? And reactant is uncharged, right? Reactant is not charged here, but here we are getting intermediate charged species, right? That means electronic difference is present here, electronic effect is present because the charge difference is there. Along with the electronic effect, here steric effect is also present, because this R group will also alter the reaction to give the product. So here if the R group is bulky, again it will give the same effect compared to the reaction in acidic medium. So because here both the effects are present, so the log kx and kme in basic medium will become equal to sterics plus electronics effect, right? In previous case we have only electronic effect, steric effect es, right? Here we have both the effects. So what will be the equation become for electronic effect? So the electronic equation will become electronic effect equation log kx by kme by in basic medium, this term, right? This one, and minus log kx by kme in acidic medium. As I told you, in acidic medium only steric factor is there, right? So if from basic medium steric will be getting minus, you will get the electronic effect, right? After subtracting the steric effect from basic medium, uh, basic medium equation, you will get the only electronic effect. And this 1 by 2.48 is a just a number to compare the Hammett and this Taft equation. Okay, so this will be the will become the equation for electronic effect. Now this is a Taft parameter. So as we have discussed, this this is here we have both the electronic and steric effect table. So when the H is H proton, so the steric effect will be less, right? As I told you, if the R group is smaller than the methyl group, it will give the less steric hindrance, that means more positive value of ES. So that's why here we are getting positive value of ES, right? And we have talked about the basic condition case also, where the sigma star value is high, because when H group is present, then the charge on the both the reactant and intermediate will also be observed, and by which we can see this more value will getting managed by basic effect, right? In basic effect, steric plus electronics we have. So if steric value is higher, that means the electronic effect will become lower. Right? How to calculate the electronic effect? I hope all of you know this equation. So here we have discussed the comparison. Now when the ethyl group is present, that means it is a bulkier than the methyl group. That means it will give a negative value of ES. Now isopropyl group is also a bulkier, so it will again give a negative value. Then third butyl group is also giving negative value, and this CH2 phenyl group is also giving a negative value. But here phenyl group is giving a uh, greater magnitude of minus value, that is 2.55, which is higher in this table. So maybe it's giving a much bulkier effect compared to the third butyl, that's why it's giving a higher value, correct? Now uh, now we will use the TEF parameter in a reaction. For any given reaction, like we have discussed this equation, this is the log kx kme in acidic medium, which is giving a ES, and 1.248 log kx by kme b minus log kx by kme in acidic medium, which is equal to sigma star. This is the relation between both the effects. And here this is the relation between both the effect. This is steric and this is, sorry, steric, which is present only in acidic medium, and this is the electronic, which is present in basic medium. And this equation is for the TRAF parameter for basic medium reaction. Basic medium reaction. So here rho star sigma star is your electronic effect, and delta ES is your steric effect. Now use of draft is example is given here. We have here alkene as a starting material substrate, which is undergoing a radical reaction. So now when the radical reaction is taking place, the homolytic cleavage will take place at this position, double bond, and we will get two radical generated here. Then this secondary radical will be trapped by uh, this X radical. So here you can see that in intermediate, two type of radical generation is taking place. One is primary and the second one is secondary. So in the beginning of the live session, I have discussed with you that the carbocation and radical stability are similar with each other. That means primary carbocation and primary radical are less stable compared to the secondary, and which is compared to the tertiary carbocation and radical. That means the tertiary carbocation and a tertiary radical are the most stable species, whereas the secondary carbocation and secondary radical are more stable compared to the primary one. right? So here, because we have here primary and this one is secondary, that means this one is more stable. Secondary one is more stable. Sorry. So as we know, this one is more stable, intermediate, and here we will see the effect of R. Now, because this is the alpha position and this is beta position, when both the substituent are R, this is the case where the substituent R is present on only one side. Now both the substituent present on both the side R, that means it will become similar, right? It will be the both the radical stability become similar, but the trapping of X radical will takes place here. Now here beta radical will generate, correct? Now you can see here beta position delta value is less compared to alpha position. Why? Because if radical will generate over here, it it will become tertiary radical, right? Now if radical generation will takes place here compared to here, it will more stabilized and it will become positive value. It will give more positive value compared to the beta position, right? That's why here you can see in Taft parameter beta position have less value compared to the alpha one. So this is the use of Taft parameter in reaction. You can find out the substitution at which position is taking place by stability of radicals and beta Taft parameters value. Now till here we have discussed the Hammett principle in terms of sigma, sigma plus, sigma minus, and then last we have discussed the Taft parameter, which is denoted by ES. The Hammett plot was applicable for benzoic acid, whereas the Hammett sigma plus and sigma minus was useful for phenol ionization and SN1 reaction mechanism. And while talking about the Taft, it was used for hydrolysis of methyl acetate. So in Taft parameter, we have discussed the steric and electronic effect, whereas in case of the Hammett, we have discussed the resonance and inductive effect, right? Now we will discuss the solvent effect. All of you know that whenever we are doing some reaction, we are putting some reaction, we are using solvent. Some rare cases are also there where we are not using the solvent, that is solid state reaction or sometime neat reaction, but most of the cases we are using a solvent which is playing a very important role in a reaction. So solvent, does solvent affects the reaction mechanism or it is just adding for uh, dilution? So we will discuss in detail here the solvent effect. Organic reactions are carried out in solvents. So there are two types of solvent: protic solvent and aprotic solvent. So as name suggests itself, protic solvents means proton should be there. So it can easily give the proton. The solvents which can easily donate the proton is called as a protic solvent. So as it's giving up proton easily, so it will be polar only, right? Polar. So, because protic solvents are easily giving a H plus ion, H, these are polar solvents and large dipole moment is also there. And large dielectric constant will be there. So, these so in this class protic solvents, some solvents are there like alcohols, amine, acid, and water. They are protic solvents. Now talking about the aprotic solvents, aprotic solvent means solvent which don't have H plus ion. Proton is not there. So now in aprotic solvents also there are two classes, that is polar and non-polar. So polar classes means the bond present in this type of molecule will be polar. So large dipole moment will be there if polarity is there, right? So the example is given here: DMF, DMSO, and acetonitrile and acetone. So here the structure is there. You can see electronegativity difference is that dipole moment is present in all these cases, right? And they are aprotic solvent because they cannot give proton during the reaction. Now talking about the non-polar aprotic solvent, where alkanes, alkyl halide and ethers are comes here. Mostly THF and diethyl ether used in this type of reactions. So this is a solvent effect on equilibria. Suppose this is our reaction, keto-enol form is given here, right? This is the keto form and this one is enol form. So in gas phase, when no solvent is present, that time equilibration is in zero point 0.4 direction, like it is more towards the enol side, more towards the enol side, right? But when the solvent we are using in this reaction is cyclohexane, it is shifted towards the keto form, slightly, not more, but slightly shifted towards the keto form, like this we can show. Sorry. Right? But when instead of cyclohexane, when solvent is replaced by chloroform, the effect is increases on keto side only. That means when the polarity is increases, you can see here cyclohexane is less polar compared to chloroform, and acetonitrile is more polar. Then again water is more polar. So while we are increasing the solvent polarity, the keto form is become stable here. So that's why solvents affects the equilibria. So you can see here, if we will switch to the less protic polar, non-polar solvent side, we will observe the enol form as a stable form. But when we are switching to the polar solution, polar solvent, we are observing the keto form as a stable form, right? So here we will discuss the stabilization of transition state versus reactant solvent effect. So now suppose we have here two types of reactions and transition state is stabilized more than the reactant, right? Here transition state is there and this is reactant. So suppose we have A as a reactant and TS is our transition state. But when we will increase the solvent polarity, what happens here? Starting material reactant stability will be higher compared to the previous case, right? Stability will increases, but the stability of the transition state will increases more compared to the reactant. As we have mentioned here, transition state stabilize more compared to the reactant, right? If the polarity is increases, that time transition state is become more stabilized compared to the reactant. So that means the hump or the height of the hill will become low. That means activation energy will become low, right? Lower activation energy. So that means delta E, delta E1 means the difference between the previous transition state and the energy difference. Sorry, this is the energy difference between the previous transition state and the transition state occur in polar solvent, and this is again the difference between the reactant energy in previous case and the with polar solvent. So the delta E1 will be higher than the delta E2, right? All of you can see here. And the second case is also there, where the reactant is stabilized more than the transition state. So when the polarity of the reaction is increases, that time reactant stability is increases more compared to the transition state stability, right? So here you can see the activation energy is become higher because transition state is lowering very small in energy, while the reactant it become more stable compared to the transition state. So the energy activation energy is become higher, so E2 will be higher than the delta E1, right? All of you understood this one? Now we have here reaction example. So here suppose we have here CH3NR3 reaction with positive charge. So here you can see this is a charged species, right? And OH minus is attacking on this methyl group carbon, uh, and this will generate the intermediate which is given here. This is a SN2 type reaction. Both the reactions are SN2. You can see here directly attack is taking place. So because this is a SN2 type reaction and we are getting this intermediate where we are showing the breaking bond making simultaneously. So here the charge is distributed, right? Charge is distributed, but here you can see we have a charged species as a reactant and charged species which is attacking on methyl group. So both the species are charged, and this is a dispersed charge compared to the starting material and nucleophile. So this is the less charged species compared to the starting material and nucleophile. So that means polarity of the solvent will affect more. Effect of the polarity of the solvent will be more on the reactant compared to the intermediate, that is transition state, right? So that means if we will increase the polarity of the solvent, it will increase the stability of the reactant compared to transition state. So reactant stability will become more here, and transition state stability will be less only because of the dispersed charge here. With the increase in polarity, charged species is getting stabilized. Always remember this one. Whenever we are increasing the polarity, charged species stability will be increases. So here, because reactant have charge present on the reactant compared to the intermediate have dispersed charge, and reactant have more charged species. That's why the stability will be increases, and that's why the activation energy will become higher, because transition state energy is lowering very less compared to the reactant one. So that's why the increase in activation energy will take place, which leads to the decrease in rate of reaction, right? Decrease in rate of reaction. Now in the second case, here again we have the SN2 type of reaction, but the difference is that here we have neutral reactant, here we have charged species. But while talking about the intermediate, here you can see it is a again dispersed charged species, right? As we have discussed in rate equation, SN2 reaction is depends on both the uh, both the reactant present in the reaction, like OH minus also nucleophile concentration as well as reactant, right? So here polarity of the solvent will affect this on depends on this reactant and nucleophile also. So because nucleophile is a charged species and this is reactant is neutral species, right? But intermediate is dispersed charge species, so it is less polar compared to this one. So the energy of the transition state will be uh, decreases very slightly compared to the reactant one. Reactant energy will decrease, but not as much as in first case, because here both the species are charged one. Here only one species is charged one, that's why it will decreases here. And transition state difference will be very low, very slight. That's why here also the increase in activation energy will be observed and the rate will be decreases. Now here we are talking about the solvent effects again. So now suppose we have nucleophile and it is attacking on our reactant, and leaving group is eliminating, right? So here you can see this is a charged species, right? Intermediate is showing a dispersed charge species. It's a dispersed charge, and both the nucleophile is negatively charged and reactant is neutral. So we have discussed in this case already here. So this is the case where the rate will be decreases. Now the second case, both the nucleophile and reactant are neutral, that means no charge, but the transition state have uh, dispersed charge. Right here there is no charge, but here we have charge. So as I told you, whenever the charge species is there, the energy of the charge species is become lower. Right, energy of the charge species is lower. So here we have neutral. Suppose this is our normal A. For second case I am writing here transition state. And now because it is neutral, there is no change will be there, but the intermediate, which is transition state, have a dispersed charge species, so the energy will become slightly lower. Right, transition state. Now you can quickly observe here that the activation energy is getting decreased. Activation energy is getting decreased. So when the activation energy is low, that means the rate will become high. Rate increases. Right. So that's why the second case is showing the increment in the rate of the reaction. Now talking about the third case, here both the species are charged species, which is more charged compared to the intermediate. That's why rate will get decreases. Now in last case also it's a charged species, so that's why again we will observe the same effect. Rate will get decreases. So here another example is given here. So this was we were talking about the SN2 mechanism. Now let's talk about the SN1 mechanism. So this is an example of SN1 mechanism. Suppose we have here reactant uh, Cr3R is any alkane group, alkyl group, and bromide. Now carbocation formation will take place in first step, right? Because it's a hindrance. CH3 group is not there, so because carbocation formation will take place, that's why it will go via SN1 reaction. Now in SN1 reaction, because carbocation formation is taking place, which is stable intermediate, right? Stable intermediate. Then we will increase the polarity. We will see here starting material reactant is uncharged species. There is no charge on reactant. While talking about the intermediate, we have carbocation, that is charged species, right? So if you will see the transition state, there is a breaking of bond and partial positive and negative charge is present. That is dispersed charge species is our transition state. So because the polarity is increasing here, so polarity will increase the charge species stability. So this is neutral, that's why its stability will not that much affected, but because this is our transition state, which is charged species, its stability get reduced, and because sorry, its stability become high and energy get reduced. Because of low energy, that activation energy will become low here. Right, activation energy barrier will become low. So that's why rate of the reaction will become high. Low activation energy means more rate of reaction is high, right? So that's why in this case solvent polarity increases the rate of reaction. Okay, so I hope all of you are clear till here. If you have any question doubt, you can ask me now, otherwise we will solve some previous year questions. Any question? Okay, so now let's talk about the question. First question is the correct statement for the given reaction if with raw value of minus 4.48 is. So first of all, you should find out the reaction pathway, right? On which pathway this reaction is depends, like SN1 or SN2, which type? Yes, SN1. Why? Because carbocation formation will take place here, right? Which is stable. So the option is given here. The reaction follows an SN1 mechanism. This is the first correct option. Now again we have given here. We have to check other options also if they are correct or not. So the second option given here, the reaction rate will significantly increase with increase in a solvent polarity. So is it correct or not? You can see here this is uncharged species and intermediate will be carbocation which is charged species, right? So from uncharged to charged species we have discussed here the transition state energy will be lower in compared to the original energy, right? So when we are increasing the polarity of the solvent, the transition state energy will get lower, so activation energy will get low and rate will become high. So the second option is given here, the reaction rate will significantly increase with increase in a solvent polarity, which is correct for the SN1 mechanism, right? Now the third sentence is here, the reaction rate will not change with increase in solvent polarity, which is incorrect, right? Again, the fourth option is the reaction rate will decrease with increase in solvent polarity, which is also incorrect. We have seen in previous example. And the last sentence is the reaction follows an SN2 mechanism, which is also incorrect. So the correct option for this question is first and second only. All of you got it? This row value negative is showing a X group is electron releasing group. So electron releasing group is stabilizing carbocation as we have discussed earlier, right? So this is a stable intermediate also. So that's why it's favoring the SN1 mechanism. Now the question number 2. The correct statement for the given reaction when the solvent is changed from methanol to DMSO is. Now you can see here from methanol to DMSO means its polarity increases or decreases. Anyone? We have discussed here. Alcohol are protic solvent, DMSO are aprotic, and polarity is also more in methanol. What will happen? The reaction rate decreases as polarity is decreases. Wait. So here, what's the reaction? First of all, see, this is a SN2 reaction, right? SN2 reaction. That means this is a neutral species and this is a charged species, and transition state is there will be low and less energy change compared to the reactant, because the reactant is charged species, so the energy difference will be higher. That means activation energy will increase with polarity, right? Activation energy will increase with polarity. That means rate will become low. The reaction rate will be low, right? With increase in polarity. We are talking about with increase in polarity. Now here you can see the solvent is changing from methanol to DMSO, means polar to non-polar. Here we have discussed the case where we are talking about the non-polar to polar, but here the question is from polar to non-polar. That means the reaction rate will be increases. If polarity will increases, that time reaction rate will decrease, but here polarity is decreases, that means reaction rate will increase. All of your understanding? We were discussing on the based on the concept based on polarity increases, but here polarity is decreases, that means reaction rate is increases. So mechanism, explanation is given here. The reaction follow an SN2 mechanism. Methanol is a polar protic solvent that stabilizes the nucleophile greater than the transition state, as I told you here. And DMSO is polar aprotic solvent that cannot stabilize the nucleophile. So I hope all of you understood this question also. Now the next one is SN1 reaction are favored by polar protic solvent, right? So here the TAF parameter meter ES measures what? In TAF parameter, what we have observed, ES measures steric effect. All of you know that? In TAF parameter, ES was stands for steric effect. Correct? So that's all for today's class. If you have any question, any doubt regarding this, please ask now only. Otherwise, we can discuss in next session also. So I'll give the brief summary of today's session. So today we have discussed the Hammett principle, where we have observed that the positive and negative slope, and we have also observed that the electron rich group was stabilizing the carbocation formation in SN1 reaction. That means SN1 reaction was stabilized by electron releasing group. Then we have observed that the intermediate if the intermediate is negatively charged, and the raw value is more than 1, that time the reaction is more sensitive than the benzoic acid. And when if the case is reversed, like raw value is less than 1, so then the reaction is less sensitive than the benzoic acid. Then we have also observed that the if raw value is equal to 0, that means there is no effect of substituent present in the particular reaction. And we have seen that if raw value is less than 0, that time the intermediate is positively charged, right? Now we have discussed some examples also today, uh, that is SN1 reaction type. So we have taken a simple reaction where both the R group was Me. In that case, the reaction was proceeded via SN1 mechanism, but when both the R group was H, that time it was followed the SN2 mechanism. But in SN1 mechanism, the slope was higher, as magnitude of the draw value was higher compared to the electron with SN2 mechanism, because the carbocation was stabilized by the electron releasing group, and which was giving a high magnitude of the raw value. That's why the SN1 mechanism was the favorable mechanism for this type of reaction. Then we have discussed another example where we have discussed two type of mechanism, again SN1 and SN2, and we have observed that the raw value was minus 5.09. So if we will find out the mechanism for this particular reaction, we will observe that this minus 509 value of raw is showing that electron releasing group is stabilizing the carbocation formation over here, right? So that's why from this experiment we can conclude that the reaction is following SN1 mechanism, not the SN2, because magnitude is higher here. Then we have discussed the again the Hammett value, Hammett raw value. So we saw here phenoxide ion was more stabilized by electron withdrawing group compared to the electron rich group. So we have observed that phenoxide ion stability was increases when there is electron withdrawing group present, and it decreases when the electron rich group is present. So we can see here The activation energy is also decreases as its at electron rich group is present, right? Because the activation energy is getting decreases for destabilized reactant. So in a destabilized case, we observe that Kx was less than K. In destabilized case, we observe that Kx is higher than the Kh. That's why magnitude of this raw value will be higher, and X will be your NH2, that is electron rich group. In other case, we have observed that the because the activation energy is increases for the electron withdrawing group, Kx is less than Kh and X is a nitro group, right? So here, because again Kx is less than Kh, the slope will be negative. Slope will be negative, and it will give a small value compared to the electron releasing group. So that's why we will observe here less value, minus 0.95, less magnitude. Then we have observed that we have summarized the Hammett equation. For the Hammett equation, the equation is log kx by kh, which is equal to rho sigma x, and we have also observed that the Hammett plot is a plot of log kx by kh versus sigma, and we can use the Hammett plot to get the information about the intermediate and transition state, and we can distinguish between the mechanism also by applying Hammett equation. Now we have taken the example of uh, reverse case, like here electron releasing group are electron rich group are stabilizing the intermediate, while the electron withdrawing group is destabilizing the intermediate. So here again we will follow the same trend we have earlier discussed. Electron withdrawing group will give the less activation energy, that means the Kx will become higher than the Kh, whereas in case of the electron rich group, Kx will be lower than the Kh. So we will observe the plot like this positive slope, which is, that means it is more sensitive than the benzoic acid. Then we have done the application of Hammett plot. So we have done the we have taken the reaction which mechanism we can predict via two pathways. Pathway 1 was there when the proton was abstracted by the OH minus, sorry, which was giving a phenoxide as a as an intermediate via rate determining step. So this is the step where which is the slowest step and rate determining step. And in the second pathway we have observed that OH minus is attacking on carbonyl carbon to give the tetrahedral intermediate, which is also a rate determining step and slowest step. So while comparing both the steps, we have observed that this negative charge species is more stabilized by the electron withdrawing group here compared to the second pathway. Like here, this negative charge is far away from the this substitution at para position, which is giving a less effect on this intermediate compared to the this one. So this one is more stabilized. That's why it's giving a more positive value, which is 2.62 and more sensitive compared to the benzoic acid. So that's why we can predict here pathway A is followed by the reaction to get the corresponding product. Then we have discussed the new scale of Hammett, where we have discussed that in previous case Hammett scale was based on a, yes, who have raised the hand? Any question? Okay. Huh. Then in previous case we have observed that Hammett plot is talking about the benzoic acid basically as a Hammett plot is talking about benzoic acid, and which is taken as a standard, and we are changing the different substituted para and meta position. But when talking about the phenol type of group, phenol group, here you can see the negative charge is in conjugation with the aromatic ring. But in benzoic acid, it was far from the benzoic aromatic ring. It is the negative charge or charge species is far from the aromatic ring. That's why, because it is more stabilized. Phenoxide ion is more stabilized because it's participating in a aromatization resonance structure, and it's a resonance structure and participating directly in the aromatization. That's why it is highly stable. So that's why the new term introduced to find out the value of these Hammett constant. So the new term is sigma plus and sigma minus. So as I told you, sigma plus is showing that electron releasing group presence, which is increasing the stability of the carbocation present formation at alpha position. This is a SN1 type of reaction. So that means sigma plus is giving a value for SN1 reaction, Hammett value for SN1 reaction, right? So as you can see, more the effect of electron rich group, the more the value of sigma plus, and negative charge is written here to avoid the confusion between the electron releasing and electron withdrawing group. That's why negative charge is introduced here, but the value is increases, right? Then we have compared all the delta plus charge values, and then we have observed that in case of the phenyl group, as a substituent, here substituent instead of electron rich group, we observe that it increases the sigma minus effect also. Why? Because in case of the sigma minus, that means here O minus will be generated. Here it is more stabilized by phenyl group compared to the H1. That's why it's giving a slight positive value. If phenyl group will be present here in O minus species, this type of reaction, it will stabilize the molecule. That's why. Then we have observed that all the electron withdrawing group are stabilizing the negative charge here, and stability is getting increases, right? Then we have discussed the deviation of from linear free energy relationship, and we observe that two type of mechanism is observed for the following reaction. Now we have two raw value minus 4.4 and 2.5 for electron withdrawing. So which one is possible mechanism for which Hammett constant? So for the first case, where the electron withdrawing group increases the electrophilicity here, it will increase the electrophilicity of this carbon atom, carbonyl carbon, which is favored the reaction, and which will give the positive value of Hammett, which is showing the increase in uh, sensitivity of the reactant compared to the benzoic acid, right? While talking about the second case, here electron releasing group will stabilize this intermediate more compared to the this one. So here electron releasing group will stabilize this positive charge. That's why this is the mechanism which will give the Hammett value of minus 4.4 for electron releasing group, right? Then we have discussed both the graph, and we have observed this is the Hammett plot we observe by this reaction. The more favorable reaction was this electron releasing group will favor the second mechanism, electron sorry electron yeah electron rich group will favor this second mechanism, while the electron withdrawing group will favor this mechanism, correct? Now we have discussed the summary, and we have discussed all the constant Hammett, sigma, sigma minus and sigma plus. Then we move towards the Taft parameter, and in Taft parameter we observe that there are two types of effect, that is steric effect and electronic effect. So in SN1 reaction we observe that In acidic medium reaction, in acidic medium reaction, we observe that here the electronic effect is zero, where the steric effect is present here, because steric hindrance will affect the rate of the reaction. So according to the Taft parameter, the equation is log Kx by Kme, which is equal to Es. Es is representing here steric effect. So if the R group is smaller, that time Kx will be higher than the Kme and Es will be positive value. But if R group is a large group or a bulky group, then Kx will be less than the Kme and Es will be less than 0, that is negative value. Then we have talked about the reaction in basic medium. So here we observe that in basic medium we uh, we have charged species as an intermediate, and reactant is uncharged. That means here electronic effect is present. Both are not the similar. So electronic effect is present. That means along with that steric effect is also present. So the equation will become log Kx Kme in basic medium is equal to steric plus electronic effect. So to find out the electronic effect, this steric effect will get subtracted by this log Kx by Kme in basic medium. So steric effect is nothing but the Taft parameter of acidic me acidic medium, right? In acidic medium. So that's why the sorry that's why the Taft parameter in basic medium minus acidic medium will give the electronic effect value, and this is 1 by 2.48 is a relation with the Hammett constant. So now here we have seen the example where we have different electronic effect and steric effect. So when the H atom is present instead of R, that means it is a less than, smaller group compared to the methyl, it will give a positive steric effect value. So that's why it's giving a positive value. When the steric hindrance is increases, that time the Es value is decreases. So we have observed here decrease in the energy. So here phenyl group is showing more bulky group compared to the tert-butyl group. That's why it's giving a more negative value, right? And electronic effect is also here given, which is also decreases. And in case of phenyl and benzophenyl is ben, is increases, right? Because of the resonance here, aromatization. Then we have used the Taft parameter for the reaction. So this is the revision again. This is the basic medium equation. This is the equation for acidic medium, and this last equation is for electronic effect equation. Then we have discussed the radical reaction where we are using a Taft parameter. So here primary radical and secondary radical generation was taking place, where the secondary radical was more stable. But when we have talked about the second case here, yeah, second case here, we are observing that alpha position is more stable compared to the beta one, because beta radical is secondary and alpha will generate a tertiary radical. That's why the alpha position value is higher compared to the beta one, right? If here radical will generate, both will remain same. That's why here we are not comparing Taft effect, but here we can compare. Then we have discussed the summary. Hammett, we have till now we have discussed the sigma plus sigma minus effect and es es term, right? Then we have discussed today in today's lecture solvent effect. So there are two types of solvent, that is protic and aprotic solvent. So protic solvents are solvent which can easily give a H plus ion, and these solvents are polar solvents. Large dipole moment and large dielectric constant is there. And in aprotic solvent we have polar and non-polar solvent. polar will have the large dipole moment, and the example of polar aprotic solvent are DMF, DMSO, acetonitrile, acetone. And non-polar aprotic solvents are alkanes, alkyl halides, ethers. Then we have discussed solvent effect on equilibria, and we observe that when we are increasing the polarity, the ketoenol formation equilibration is changes. So the keto form is become more stable in more polar solvent. So as the polarity increases, keto form stability is also increases here. Then next we have discussed the transition state stabilized more than the reactant, and the second case we have taken the reactant more stabilized than the transition state, and we have observed that when the transition state is more stabilized than the reactant, that time the activation energy is lower and the reaction rate is higher. While the in other case, when the reactant stabilize more than the transition state, that time the activation energy will become higher and the rate will become lower. Then we have taken one example for to understand the term. Here we have taken the charged species and uncharged species. Both the reactions are going through the SN2 mechanism, but because the reactant are more stabilized than the transition state, we observe the increase in the activation energy in both the cases, and rate was decreases in both the cases. Then we have taken the few examples where we have observed that when the intermediate transition state for the charged species and the reactant was uncharged species, we observe the increase in rate, while in other cases we observe the decreasing rate of the reaction. Sorry. Then in another example we have seen SN1 mechanism. In SN1 mechanism, we observe that the activation energy is decreases because the charged species intermediate is stable intermediate compared to the reactant. That's why the activation energy is decreases and rate of the reaction is increases. Then we have discussed the questions, and the question was based on the solvent effect and rho effect. So because here minus 4.48 magnitude of rho is given, that means here electron releasing group will be present, and it will stabilize the carbocation formation. So this is a reaction. This reaction will follow the SN1 pathway. So option number A is correct. Then the reaction with the increase in the solvent polarity, the reaction rate will also increases, because we have learned that in SN1 case, increased solvent polarity will increase the rate of the reaction. So the second option is also correct. Apart from these two options, others are incorrect. Then we have discussed the other question where the solvent was changing from methanol to DMSO, and we have observed that this is a reaction. This reaction follows the SN2 mechanism, and methanol is a polar protic solvent that stabilizes the nucleophile here and greater than stabilize the nucleophile greater than the transition state we have shown here. And DMSO is a polar aprotic solvent that cannot stabilize the nucleophile. That means it can coordinate the cation of the nucleophile to solvate it better. So as DMSO cannot stabilize here because it is a aprotic solvent, so the reaction rate will increases because stability will not be there in reactant, and the activation energy will be lower for DMSO case. That's why the rate will increases in case of DMSO. Rate will increase in case of DMSO. Then we have discussed the third question where the TAP parameter ES measures the hysteric effect as we have learned earlier. So this is the correct option. Yeah, that's all for today's lecture. Thank you so much for your kind attention. If any question, any doubt is there, please ask your doubt and questions. Thank you so much. Okay. Okay, then